So for part three, we'll go over the kinetic terms associated with this. This is going to help understand the internal forces and can help provide an indication of the joint load and even help or explain or predict joint pain or degenerative joint changes that may occur over time. So if we understand how these forces are interacting with the patient, it can give us insight as to what the patient might be predisposed to or why they're doing this from a physiological level. So we're going to break these down in individual components, but this is just a summary of what we're going to go over. Basically, we're taking these three things together. We're taking segmental kinematics, we're taking the physical and mathematics, and external loads or forces, and this determines the kinesiology, the movement of the body, and essentially it's estimating what must have occurred internally to produce the outcome that the body is providing. And that's the thing we're observing, essentially. We're observing the movement, and we're trying to reverse engineer what may be causing that. So we're looking at the outcome of how the movement looks, and that tells us internally what might be going on with that patient and what we might have to fix or correct and those types of things. To show you how this can be somewhat confusing, if you look at the individual forces acting on the foot as it hits the ground, you can say, whoa, this is a lot of math and geometry involved and physics and tying that all together. So this is how it looks at a complex level, which these movements are very complex. So you don't need to know this. Obviously, it's on your handout, and you don't need to know any of this terminology. But I want to show you what it could look like to a physicist, and then how we're going to break that down from a physical therapy standpoint. This has to do with what's known as the link segment model. So this is going to break down the individual segments. So you can see sometimes we call this the HAT, head, arms, trunk segment. Then you have a thigh or upper leg segment, you have a lower leg segment, and you have a foot segment. In a closed kinematic chain such as this, all those segments have to interact together, a series or a chain of segments together to produce a synergistic movement that occurs. So as we look at someone with stance here on the reference limb of the right, we're taking all these segments and combining them together. So we have to look at the body as a series, but also we have to look at the individual components within that series or those segments. What are the things acting on these segments? And what are the moments acting on the segments? We know that we have this gravitational force, which is going to act downward. It's going to take the body and the center of mass towards the center of the earth. And that's obviously equal to the magnitude of the mass. So the greater the magnitude or the greater the mass, the greater the overall force, or the greater the acceleration, the greater the force. So an object with a high mass and a high acceleration is going to have a great force, where an object with a low mass and a low acceleration is going to have less force. Every force has an equal and opposite force acted upon it, and that's going to be represented by the ground reaction force, or sometimes we call this the GRF, ground reaction force. And that's going to be equal to the gravitational force, but in an opposite direction. And then internally, we know that we have muscular and ligamentous forces, and these are going to create their own internal moments. And so all these things fit together into the link segment model. Let me give you a better example. As we're pushing off from the ground, imagine you're at terminal stance phase and you're about to push off. You're plantar flexing. You're contracting your gastrocnemius, your soleus, your plantaris, tibialis posterior. You're trying to get toeing off. You're trying to go from stance to swing phase of this extremity. You could see the center of rotation is going to occur around the ankle joint. More specifically, the talocrural joint is going to be going from a dorsiflexed or neutral position into plantar flexion. And then your toes, great toe especially, is in that extended position, but now it has a flexor moment. It's trying to perform flexion. So those toes are flexing, and these are the different moment arms that are represented here. And there's acceleration going in this direction, horizontal acceleration, and there's vertical acceleration as well. And you have what's represented by the X here is the center of mass. So if it's a circle on here, usually that represents the center of something, center of rotation, center of mass. If there's an arrow, it represents some type of force component on there. C is representing the gravitational force here acting on the center of mass. And then A here is representing that ground reaction force in the alternate direction. But you can't have a ground reaction force here directly against gravity because it's not in contact with the ground. So that's a kinematic representation about the link segment model and how it fits together there. You have inertia, which is really measuring an object's resistance to change. So an object that is stationary does not have any inertia, but once the object starts to move, an object in motion will remain in motion unless a force acts upon that. So that is your inertia, and how increased mass with movement can result in increased inertia. The rate of change in relation to angular velocity is that inertia. So here's your GRF. This is the force being applied to the lower extremity, to the foot, whatever part of the foot is in contact with the ground. It could be an entire foot, could be only the heel, it could be just the toes. That represents the force opposite of gravity. And certainly with jumping or running or landing, you have a significant increase in ground reaction force. And the ground reaction force in stationary, so if you weigh 150 pounds and you're standing statically, the ground reaction force should be 150 pounds. But if you jump, let's say off of a 4-foot surface, and you're landing with 150 pounds, the ground reaction force is going to be significantly greater than 150 pounds. Could be 5 or 6 times your body weight or your mass, because you have an acceleration associated with that mass. So force equals mass times acceleration. That ground reaction force is going to now be increased related to the amount of acceleration occurring there. Another term to associate with is the center of pressure. So even though this entire surface area may be in contact with the ground, this is a pressure mapping system. So the center of pressure is going to be the center of where it is. However, that may not be the same place as the peak pressure points. So typically, with normal stance, we have a lot of peak forces going through the heel and a lot of forces going through the metatarsals. However, the center of pressure might actually be here in the middle, where there's very little pressure, more in the arch or the midfoot. So with here, and this may shift with weight bearing. So if I lean my body weight, it might shift how that is performing. You have the moment of force. This is the moment arm. Torque equals force times distance here. Some people call this torque the turning effect. It's the rotational equivalent of a linear force that's going through the body. So this is just like the previous units, just to consider this term, internal and external forces. The internal moment arms versus the external moment arms. Assistive devices may affect with Gait the external moment arms versus the internal moment arms are relatively fixed based on our anatomy. We know that energy is represented with work, and this is typically expressed in joules. The work is like torque, it's force times displacement. But in terms of internal work performed, we often relate this to oxygen consumption or expenditure, and caloric expenditure as well is a common way that we look at work, metabolic work, and we look at sometimes metabolic equivalents, METs, representing that. So a metabolic equivalent, here we go, metabolic equivalent, MET, is another way of representing that. And for different tasks, you'll see different METs associated with that. And sometimes exercise equipment will measure METs as well. Power generation, power is usually represented by watts. And so that represents the work performed over time. So if I'm doing something at a relatively shorter time, but the same amount of work, I'm going to have more power. So if I swing a hammer and it's a really slow swing, the time is going to be increased. It may take 2 seconds for me to swing that hammer. And that may be a certain power. But if I take the hammer and I swing it quickly, I swing it in half a second, the time is decreased, whereas the work may be the same, so I'm going to have an increased amount of power, increased wattage. Even though the work performed, whatever the mass of that hammer is moving through whatever distance, if that 1 kilogram hammer moved through a distance of 1 meter, that's still the same work, but time decreased, and it's an inverse relationship, so that means power is going to increase. So as we go from a faster walk, or even a run or a jog, we're increasing our power. Our work may be pretty similar in terms of walking 1 mile in distance, for example, or running 1 mile, maybe the same energy expenditure, but I'm going to do it in a faster time, so running involves more power than walking and requires different muscle fibers to generate power as well. EMG, and you could see here there's a surface EMG. It could also be done via needle EMG. That's representing the electrical activity within the muscle, especially in more superficial muscles, to determine which muscles are performing which functions and activities. And we'll go through a little bit of the EMG findings throughout, and this will be reinforced. But let me just show you a few different EMGs as it relates to the different phases of gait. So here you go. So we're gonna give this more in PowerPoint. I thought it would be a good way to introduce this. We're looking at the reference limb on the right-hand side. So this is looking at the loading response phase. So as that is loaded, you can see there's some muscle activity, glute max, glute medius. It makes sense that as the body is absorbing that closed kinematic chain, there's going to be some activity. You see lateral gastroc, tibialis anterior semitendinosus. And then you could look at the mid-stance phase. Okay, so here at mid-stance, there's more gastrocnemius, whereas the glutes are relatively quiet. So we're getting the weight transitioning to more the forefoot as opposed to the rear foot. And so the gastroc is going to consist of that plantar flexion moment. And then as we look at more into the mid-stance phase for that reference limb, the muscle activity is pretty minimal there. The left lower extremity non-reference limb is generating more activity during that. And as we get into this pre-swing phase, so now we're getting ready. So if you notice the difference here is now there's a knee flexion component there. And with knee flexion, and you're trying to get the toes off, you can see there's that tibialis anterior that's going there. But the foot and the leg is priming up for that knee flexion activity, and it's moving at this point. So tibialis anterior, we're going to go further into tibialis anterior here is active, and we're looking at, in this phase, we're looking at terminal swing and how the EMG activity is significant there. So these slides don't have the hamstring activity listed, but at least it gives you looking at the ankle activity when you dorsiflex and when you perform those different things. So we'll divide into this in much more detail next time, but I think it was good to just go through some of the phases and look how it all pieces together. So that's all three parts of the PowerPoint for this. It'll prepare you well. The main thing to be aware of coming into class is that you know the phases, and you can identify, if I showed you a picture of a phase, you could identify which phase that is, so that as we do these things, and you think about what is occurring during each phase and during the phase. Sounds good? Thank you.